Okay, so we are ready to go. So last class, we started with chapter 1, and we said that in chapter 1, we were going to make a small review of basic computer architecture. So if you are a computer engineer or a computer scientist already, or you are studying something related to that, this is going to be more like a refreshing of your previous knowledge, okay? But if you're not familiar or so familiar with any of these concepts, so obviously this is going to require a little bit more effort. So the other day, we made a small introduction to computer structure, and we established the main state of the art of the main challenges that hardware is facing nowadays, okay, such as power consumption, the idea of using the multi-core approach in order to use the extra transistors that we have available, etc. Okay, and after that, we said that we were going to divide our explanation, focusing alternatively in two of the main points of interest of a computer. First, the processor, and this was something that was already covered during last class. I know that this is a bit in a rush, in the meaning that this is something that you study in computer science engineering for a whole semester, or maybe for two different subjects. But for me, the main idea is that those that already have this knowledge refresh it or review it, okay, and those that don't have it at least have the basic knowledge required to understand the rest of this course. Okay, so today we are going to divide this class in two halves again. In the first half, I'm going to finish chapter 1, explaining or focusing my explanation in the other part of the computer, which is relevant and very relevant for the performance, which is the memory hierarchy. And after that, we are going to start with chapter 2, explaining some concepts related to the classification of parallel computers, okay, of HPC architectures. Okay, so let's start with memory hierarchy. So these are the books and the chapter of these books where you can find an extended version of the information that I'm giving you today. Okay, so if you have interest, these books are available in any of the libraries, both in University of Santiago and University of A Coruña. Okay, so hello. So when we talk about a computer the other day, we always introduce at the beginning of this explanation the concept of the von Neumann architecture. And in the von Neumann architecture, we identify the basic building blocks of a computer, which basically are the processor, the I/O, and the memory subsystem. And we mentioned at that time already that the memory itself is not like a single device that makes the functioning of a memory system, but we have several devices. So this illustration here is very good to understand why we cannot have a single memory, okay? This is measuring the gap between the speed of the processor and the speed of the memory through time, okay? So what you can see here is that, as we commented last class, the speed of the processor was increasing a lot every year. For the speed of the meaning of the processor, I'm meaning in this case the speed of a single core, and at some point, and this is the beginning of the multi-core era, the speed of a single processor or core was almost frozen, and we use the extra transistors to create multi-core processors. Okay, so this is the basic idea. Although this slows down in the improvement in the performance of a single core, we can see that the evolution of the performance of the memory is not so good, like in the case of the processor. And as you already know, the basic operation of a computer involves that the processor is executing instructions, and these instructions require to bring data from memory, okay, and to send data to memory. So obviously, if the memory is much slower than the processor, it's going to have to wait, okay, and this is going to produce stalls, okay, sorry. Stalls. So this is a term that we are going to use throughout the presentation to indicate that situation where a computer, where a computer, a processor is waiting for some information to come from memory, so it's like stop, okay, and it's degrading the performance. In order to solve this problem, well, the problem itself is that we cannot create a device which is cheap enough, okay, that is at the same time fast enough, and that has enough capacity to make the role of the memory in a computer system. So instead of using a single device made of a single technology, what we do is that we combine several technologies in several devices in order to create something that is called the memory hierarchy. Okay, so the idea of the memory hierarchy, if you remember it from our last class and also from the first class of HPC tools, is that the processor, this is the representation that we are going to use for the processor, have below it several levels of a memory hierarchy. The first levels are small, are fast, but at the same time are very expensive, okay? And by expensive, I mean that the cost, the relative cost per byte is very high. As we descend in this memory hierarchy, and we are not talking yet about any technology, we are becoming slower memory devices. We have larger memory devices. That means that we have more capacity, and they are obviously cheaper, okay? Because they are larger, they cost more or less the same, and obviously the relative cost is decreasing, okay? So we have like several levels. Leaving aside the technologies that compose this memory hierarchy, the basic operation of the memory hierarchy is that when we search for a piece of data, because the processor emits a read or write memory operation that is accompanied of an address, memory address, okay? The first place where it's going to find this piece of information is the topmost level of this memory hierarchy. The topmost level of the memory hierarchy, as we already know by the previous classes, is the cache memory. So this only can store a few megabytes of information, and if we don't find the if we find the information in there, this is going to be what we call a hit, okay? Because the information is at that level, and if not, this is going to be a missed. Okay, so we have like two different outcomes when we search for a piece of data in memory, a hit or a miss. If we find the data there is a hit, then we provide the data to the processor. So the higher in the hierarchy we find the information, the faster the memory information is going to be loaded or stored, okay? So part of the success of this approach is that most of the time we find the information in the topmost levels of the memory hierarchy. What happens if there is a miss, if the information is not in there? Then what we are going to do is to search recursively in the lower levels of the hierarchy. And in each one of them, we can still have a hit or a miss, okay? If it is a miss, then we have to continue our search lower in the memory hierarchy. Another important point is that when something is not found, for instance, at this level and at this level of the memory hierarchy, and we need to bring it from here, for instance, then instead of loading just the piece of information that is required at that point, okay, we are going to load something that is called a memory block that contains not just that piece of information, but also other pieces of information that are around it, okay? So this is a key behavior of the cache memory, of the cache hierarchy, and that is going to benefit something that is called spatial locality, okay? Okay, so if we think in technologies, we can think, for instance, that this is the cache, okay? And we are going to have like different cache levels, okay? 1, 2, 3, it depends on the system. This level can be the RAM memory, that is usually known as the main memory. And below this, we usually have the I/O, or what we call the disk of the hard drive. Another important subdivision of this memory hierarchy is that anything above the main memory in the hierarchy, that means the cache memory or the main memory, is also known as the internal memory of the computer, okay, or the physical memory of the computer. These are like interchangeable terms that we can use at this point. And this is made of technologies that are, volatile memories, okay? So this means that when the power goes off, then the information is vanished, okay, if we don't store it previously. And anything that is below this point, the hard drive, the USB, any kind of secondary storage, this is going to be non-volatile or permanent storage devices, okay? Okay, so this is more or less an overview of a memory hierarchy, the main points of this. So obviously, this memory hierarchy, if most of the time, let's say 90% of the time, we find the information in the hard drive, this is going to be a disaster, okay? Because we don't want the processor to have to wait for the hard drive, because the hard drive is a very slow memory device, okay? So if this happens, what you are going to notice in your computer is that it's very slow, okay? You can think in what happens when you start the computer. When you start the computer, the volatile memory levels of the memory hierarchy are empty, okay? So you start populating these levels with information. And normally, this information is allocated by programs or is loaded from the hard drive or from the disk, okay? And this takes a lot of time. Less time is true nowadays with SSD hard drives, okay, because it's a faster technology, but several years ago, it could take like 5 minutes or 4 minutes to start a computer, okay? And that's the reason why. So the more hits we have in the topmost levels, the best is going to be the performance of your computer. And this is going to be key for HPC, okay? This is very important because you can say, okay, I'm hearing an HPC master. Why are you talking so much about computer architecture? Obviously, because this is going to be very important. One thing is that you have to parallelize your program, okay? And this is going to increase the performance of your application. But if you don't work on improving the behavior of the memory hierarchy, it's not going to be worthy, okay? You need to do both things, okay? So the key of the success of the memory hierarchy is what we already mentioned the other day, is the principle of locality, okay? So the principle of locality have like two different aspects. Temporal locality, that means that when you access a piece of data, it's very likely that you access the same piece of data in the near future, okay? So when you need something once, at least once, then, as we mentioned before, not just bring it to the processor, also place it in the topmost levels of the memory hierarchy. Why? Because if the principle of locality is true, then you are going to need that information soon, okay? And the next access is going to happen faster, okay? That's the idea of the principle of temporal locality. As I told you the other day, this works at different levels. If you think in a computer, when you open the Chrome browser, one of the things that you are doing is opening the program. So you are loading, for instance, the application, the code of the application. Okay? So the first time you open Chrome, it takes some time. Okay? And the reason is that it's doing things, but also is loading things from memory. Okay? But the other day, I also mentioned that when you have a loop like this, and this is not any special language, okay, it's just pseudocode. What you are doing is accumulating all the values of array A from 1 to n in an x scalar variable, okay? So at this point, you have already some temporal locality because I, the loop variable, and x, the accumulator, is being accessed over and over, okay? This is not a great example of temporal locality because if you think in the machine code that is going to be generated when you do this, this is going to be mapped to registers, okay, of the processor permanently. You are not going to have like a memory location where you are going to store the loop variable, okay? This is going to be just one register of your processor. And with X happens something similar. You are going to have X all the time in a register. You are not going to store it every time in every iteration to memory, okay? What you are going to do is you are going to keep it stored in the register, and at the end of the loop, then probably you are going to store it in some physical address. Okay, so the other aspect that is relevant in the principle of locality is what we call the spatial locality, okay? And the spatial locality is the idea that when we access some information, it's very likely that the information that is near that piece of information is accessed soon, okay? And this works at different levels. If we are reading a big file, this file occupies lots of blocks of memory, okay? So normally this file is stored sequentially in memory, okay? So when you access the first part of the file, then it's very likely that soon you are going to access the second part, and so on. And as you can see in this example, this also works at the source code level, okay? Because in this case, the access pattern for A is that you access A0, then A1, well, or 1, and then 2, and then 3, and so on, okay? So this means that when you bring A1, as I told you before, you are not going to bring only A1, but all the block of information where it's contained. And this block is going to probably contain also A2, A3, A4, and other elements of A that are going to be needed in the near future. Okay, so when you have an application that is regular, okay, do you understand the difference between a regular and an irregular application? Can you think in numerical methods that imply regular access pattern and irregular ones? For instance, a matrix multiplication. In a matrix multiplication, you are accessing a matrix by rows and another matrix by columns. This is a regular access pattern. Do you know what sparse computation is? Sparse? Okay, when you have matrices in some areas where you have a lot of null values, okay, there are ways to store them in a compressed manner, okay, with special data structures. So this is going to generate codes that have very bad locality, okay? And the implications of this is that you are going to have a very bad both temporal and spatial locality, okay? But in any case, when you are working normally with regular codes, with regular access pattern, like the matrix multiplication, you have to investigate if the performance of your application from the point of view of memory is good or is bad. And if it is bad, then you have to find a solution for that, because this is going to improve a lot the performance of the application. Okay, so this is more or less what I told you before in my illustration, okay? And these are samples of memory hierarchies, okay? This is the memory hierarchy of a smartphone, okay, of a personal device. So this is the CPU, the processor. These are the two levels of the cache, which are private to each core. This is the memory, the main memory, the RAM memory that the phone has. And this is the storage. And as you know, inside your smartphone, you don't have a magnetic hard drive. What you have is what is called a flash memory. That is basically the same technology that is used for SSD hard drives. Okay, and as I told you, I believe in HPC tools, normally they are composed like something called system on a chip, because we have a chip where the whole system, or most of it, is contained. Okay, so this is the memory hierarchy, but for a desktop computer. And well, in this example, we have like a different memory hierarchy for a desktop computer for a server. But I believe that this is mostly deprecated, and that now computer for a server. But I believe that this is mostly deprecated, and that nowadays most desktop computers have this memory hierarchy, okay? Because if you have a desktop computer, maybe not your laptop, okay? But most desktop computers have a CPU with several cores. Normally, the two first levels of the cache are private, and to each core, and the third level of the cache is shared among all the cores, okay? Then you have a certain amount of main memory. Okay, maybe this is the amount of RAM memory that you have in Finisterrae, but not in your desktop computer. I have 32, okay, but it's not usual. I mean, most of the people has like 16 or something like that. And then you usually have like two different storage devices. One SSD for the programs and things that have to be fast, okay, the OS and things like this. And then for files that occupies lots of space, like movies and TV shows and things like this, then you have like a secondary storage made of the traditional magnetic technology, which, as you know, is slower, but is cheaper, okay? And you can get more space for the same price that an SSD hard drive. Okay, so this is an indication of the memory technology. This is the cache memory, okay? This is the cache memory. This is the latency in nanoseconds. I don't know how updated are these values. Okay, probably these values are from 2019 or something like that, 2 years ago. And this is the cost of the cache memory per gigabyte. Okay, obviously it's very high, but you don't have 1 gigabyte of RAM memory. You just have a few megabytes of information. The dynamic RAM is the technology that is used to implement the main memory. You can see the difference between the latency of the cache memory and the dynamic RAM. And you can see that it's already a drama, okay, to have to go to the main memory. Maybe you are not going to notice, but if you are doing it all the time, probably this is going to imply a big difference in the performance. And this is the cost per gigabyte, okay? This is the latency for a magnetic disk, which, as I told you, is quite slow. Notice that here we are changing the unit from nanoseconds to milliseconds, but obviously the price also drops dramatically, okay? And obviously this is a great improvement. Okay, so obviously if we were able to ask for a wish, okay, to a magician or something like that, we will ask for something which is as cheap as the magnetic hard drive, that has the access time of the static RAM, that is the cache memory, okay, and this is not possible, okay, and that's the reason why we need the memory hierarchy. Okay, so common principles apply to all levels of okay, so let's talk about the memory hierarchy. So we already explained which is the basic operation and layout of a memory hierarchy, okay? So having this into mind, I understand that we have to take several decisions or to establish like several policies. The first one is when we bring something, a block of information, to a level of the cache, where we put it, okay? In which place we put that information. And this policy is going to be called block placement. Also, we don't have a guarantee that the information is at a given level. So we have to understand how to find a block, for instance, in the cache, to be able to know if the block is in that level of the cache or not. Something that I didn't mention before, and that is a little bit important. Okay, let's change the part of this. Okay, is that the cache memory is a type of memory which is associative, while the RAM memory is a type of memory that is called random access memory. Do you know the difference between these two types of memory? Anybody? What? No, between the idea of an associative memory and a random access memory. Okay, in programming, do you know the difference between a hash table and an array? Do you know what a hash is? A hash is like a dictionary, okay, where you can find or search information for a key. Imagine I have a hash table with several cities in the world, and its associated population, okay? And I put population Madrid. And if it has information, it's going to give me that information. If not, it's going to write an instruction that this information is not available. So this is an associative cache, an associative memory. The idea is that when we search for a memory block in the cache, we are going to search for it, but we don't know if it is in there. Okay, so sometimes we are going to have a hit and sometimes a miss. However, in an array, we have the information indexed by a number. And if I don't exceed the size of the array, I have the guarantee that this information is there, okay? Can be accessed there. So this is what we call a random access memory. If I have a physical memory address, this memory address corresponds to a single position in the random access memory, in the main memory. So if it tells me the 0 position, that's the beginning of it, okay? Or another position in the middle, is another position in the middle. But I have the guarantee that if I have an address, this address corresponds to a position in the main memory. So one question that maybe arises in your mind at this point is, okay, so if the processor emits a physical memory address, I have the guarantee that this memory address is in the memory, in the main memory, in the random access memory, okay? Because it's what I have just said, okay? That if you have an address, and this is a physical memory address, this corresponds to a position of the main memory, of the random access memory. But before I told you, sometimes the information is not in the main memory, and you have to search for it in a lower level of the memory hierarchy. Why is that? Okay, if you didn't study computer science, you don't know for sure the answer to this question. But if you study, maybe you are aware of something that we are going to talk later that is called virtual memory. Okay? So the trick here is that programs never emit physical addresses directly. They emit virtual addresses. And these virtual addresses are translated into physical ones. But sometimes the translation is not possible because the information is not loaded currently in the physical memory. Okay? So in that case, this is going to be a miss. But we will talk later about the involvement of virtual memory in this process. Okay, but for now, another problem that we have to solve is what is called the replacement policy. The replacement policy is used when you have, for instance, a cache level full of information and you need to load a new block. Okay? So you have to decide which block to be replaced to make room for the new one. Okay? Like I have everything occupied, okay? and I have to load here new information, so I have to decide where. And you can think that this is a trivial decision, like, okay, pick one randomly. And actually, picking one randomly works fine, okay? But there are smarter ways to do it that allows to improve the performance of the memory hierarchy. Why? Because they are aware of the principle of locality. So there are policies, I don't know if you know one, that is called least recently used. That is basically the definition of the principle of locality. When you, I don't know, if you have shoes in your house and you have like 4, I don't know, 10 spots for shoes, and you buy new ones, okay, then you have to take to the through to the bin trash any of them, okay, that you have. So which will you pick? Those one that you don't use usually, okay? So that's the same idea. If I see that a piece of data is not often used in the last nanoseconds, okay, so obviously are going to pick that for replacement. And also, we have to decide something that is called the grid policy. The idea of the grid policy is very important because it's necessary to keep coherence between the data in the cache and the data in the main memory. And you will see later in this same course that this is going to be even more complicated in the case of multi-core computers, because in multi-core computers, you don't have a single cache memory. You have one private cache memory per core, okay? Okay, so this is more or less what I explained before. Okay. Okay, so regarding the writing of the cache, this is the first problem that we are going to solve. So let's simplify things. I have the processor. I have the I have the processor, I have the cache, and I have the main memory. So I have the information that I'm going to write. I have a copy in the cache and a copy in the main memory. So the question is, if I write something in this position, should I write at the same time the cache and the main memory, or should I write just the cache and later, when this information goes away from the memory, to update the copy in the lower level of the memory hierarchy? Okay, these are two different policies. If I update the two copies, this is called write-through. What is the problem of write-through? Which potential problem you see? Because it's the most straightforward approach. I mean, if I want to keep things coherent, I should write both copies. But what's the problem with that? Yes? Yes, yes. So that's the problem. That if you are writing all the time the same memory position, you are going to make n writes in the cache and n writes in main memory. Okay? And as you know, the performance of the main memory is worse than the performance of the cache. However, if you just update the copy of the cache, then this is called write back. Okay? So this copy for a time is not coherent. Okay? But you have a mechanism that says when this information is replaced from the cache, then update the copy in the main memory, only at that time. So in the situation that you mentioned before, using write back, you are going to have n writes here and one write in the main memory. Okay? Okay.
When the data will change in the main, at which time?
Yes, before we said that the information is kept on the cache while it's not replaced. I mean, the cache is always loading information, and at some point, this information is not going to be interesting anymore for the program, so it's going to be replaced from it. Normally, when it's replaced, it's just removed from there. But in this case, you have to have an indication that this information was modified. And then, if you check that, then you are going to update the copy in the main memory. Okay, so you pay the price of updating the information in the main memory just once, okay, which is obviously a big performance improvement. Okay, so before, when we were explaining the cache and the memory hierarchy in general, we mentioned that we can have two situations: a hit, when the information is found at a given level, and a miss, when the information is not found at a given level. So obviously, something that we have, or we are going to try, hit or a miss, that we are going to try to keep under control is misses, okay? Because we want that most memory accesses are hits in the topmost levels of the memory hierarchy. So in order to understand misses, we have to classify them. Okay, this is something that is done in many topics. When you want to study something, the first thing you do is a classification. Okay, so it's the same for cache misses. So there are like three types of cache misses, depending on the reason. Compulsory misses happen because memory is volatile. So the information has to be loaded there for the first time, sometime. So that's the reason why they are called compulsory misses, okay? Because the information has to be loaded for the first time. In any other case, what happened is that the information was loaded once in a time, okay, some time ago, but at some point it was replaced from the cache because the cache was full. The cache decided that this information was not relevant, and it removed it from the cache. If the reason for this decision is that the capacity of the cache is not enough, then this is a capacity miss, okay? For instance, I'm accessing in a loop over and over an array of 64 kilobytes, and my first level of the cache have 32 kilobytes. Obviously, it doesn't fit, okay? So the problem is the capacity of the cache. Conflict misses involve that you have to understand how the placement in the cache works, okay? But I don't believe that it is realistic to explain this in just a few minutes, okay? So I'm going to skip that. But basically, there are some situations where the memory access patterns is unlucky, and this happens a lot, by the way. And then, although you have room in the cache for all the information, all of them is conflicting in some cache position and is kicking out from the cache to each other. Okay, so this is a problem that can be detected and avoided. Okay, so cache optimization, and this is from the point of view of the architecture, okay, because obviously I know that in HPC tools you started to see some source code level optimization that targets the cache performance, okay? But in this case, we are talking about how to change the architecture. For instance, larger block size, I mean that the block of information that you load when you load something in the cache is going to reduce compulsory misses. Because when you load something, you are load more information with it, okay? And this naturally is going to reduce compulsory misses. The problem with that is that it can increase conflict misses, okay? Because it can produce more conflicts. Another possibility is to increase the capacity of the cache. And you can say, okay, so this is the great solution. I can increase the capacity of the cache until 1 gigabyte. Why, instead of having 1 megabyte of cache, I don't have 1 gigabyte? Well, first, because the area of the chip is not enough. Second, because the static RAM technology is not so scalable. And also, third, because your processor, only the processor, will cost like $6,000 or something like that. Okay, so this is not affordable. And also because it's going to increase a lot power consumption. Okay, so I'm going to skip this because I decided not to talk about associativity and cache placement. And another idea that obviously is applied is to increase the number of cache levels. Okay, some years ago, like 30 or something like that, a processor had a single level of cache. But at some point, they decided to divide the cache like in several levels. Okay, the idea is that you can have like a very tiny first level cache where you put everything that is being heavily used by the computer at that point, okay? And this is going to match almost the speed of the processor. But if you miss that cache and you have to go to the lower level, instead of having directly the main memory, the RAM memory, you can have a second level of cache of a few kilobytes. Like the usual size is 512 kilobytes of information. Okay, and even if you miss the second level, you have a third level, and then yes, you have the DRAM memory. The reason for this is that when we talk about latency, we saw that the latencies for static RAM, for the technology of the cache memory, is in the order of nanoseconds. Okay, but when you have to go to the dynamic RAM, to the RAM memory, is in the order of milliseconds, okay? So you have to make caches as large as possible to gather most of the situations, okay? Okay, this is not very relevant, and this is not understandable at this point. Okay, block placement. I'm going to skip this because we are going to mess up with that a lot of time. Okay, so what can we do as programmers to improve cache performance? I believe that you are exploring, or you explore this possibility with Emilio in HPC tools. Most of these things are done by the compiler, okay? For instance, the loop interchange technique that I believe that you already learned with Emilio, or the tiling or blocking technique, okay? But these techniques usually trying to improve the locality. Okay, another important thing is the interactions with advanced CPUs. Something that we mentioned when we talk about the CPU at the very end of that section is that actually CPUs don't execute the machine code necessarily in order. Okay, they made it out of order in order to try to hide the latency of memory operations. So at the end, when you order a load or a store operation, this load or store operation is not going to be executed immediately. Okay? Remember that at the beginning of this section today, we mentioned that one of the problems that we have is that memories are very slow in comparison to processors. So if we stop to wait for memory every time we have a load or a store operation, that will be a drama for the performance. And we don't want this, okay? So instead of doing that, we can have these load and store operations pending, okay? And there are like very advanced mechanisms that are called reservation stations that they keep track of the pending instructions that are going to load information that is going to be relevant for future instructions. Okay? So this is quite complicated, and we are going to talk about this in the next chapter more in detail, but have in mind that one way that the processor has to attenuate the gap between the processor and the memory is to not to wait or not to stall the processor while a load or a store operation is being performed. Okay, so this figure represents a comparison between two sorting algorithms, radix sort and quick sort, for different vector size, okay, and that's the x-axis, okay, and regarding instructions per item. Instructions per item is the number of instructions required per each item order, okay? So you can see that for smaller vectors, radix sort requires lots of instructions, okay, while quick sort is quite stable. In the case of radix sort, regarding the number of instructions, is more efficient, but for larger vectors to be ordered, okay? This is another comparison regarding clock cycles. And obviously, if you have more instructions, the obvious consequence is that it's going to require more clock cycles, okay? So the evolution of both lines is almost the same than in the above figure, okay? But this is the perspective of the cache performance, okay? This is a comparison of the evolution of the cache misses per item order, okay, depending on the size of the vector to be ordered. So what can you see here? What you can observe? Which of them do you believe that have a better performance from the perspective of the cache? What? Quicksort? Yes, the second. The second is quicksort. Okay, the second is quicksort, and obviously you can see that. And actually, what you can see is that the radix sort, from the perspective of the cache, is reducing the number of cache misses per item at the beginning until a point that is more or less like the optimal point, and then it starts degrading the performance. So this is just an example of, depending on the algorithm that you use, even if you make an analysis of the algorithm in terms of the instructions that are required, or even the clock cycles that are going to be required, you also have to have into account what happens from the perspective of the cache, because this is going to be very relevant for the final execution time. Okay, just a motivational example. Okay, did you study loop tiling or loop blocking with Emilio in HPC tools? No? No? I don't know. Okay. So, did you study loop interchange? Yes. Loop interchange, the idea is that in C language, matrices are stored by rows. If you access a matrix by rows, the locality is good. If you access it by columns, the locality is very bad. So if you know that you are accessing the matrix by column, just interchange the loop, because this is going to be an instant improvement in the performance. Okay. However, in this other situation, what is this? A matrix multiplication. Okay, this is a very normal matrix multiplication. Yes, this is no. Yes, but it misses a loop. I don't know why. Okay, well, it doesn't matter. What happens in this code is that I have a matrix that is being, yes, because the I loop is not here. Okay, but there should be an outer I loop. Okay, and that way it will be a matrix multiplication. So the problem here is that we have one matrix A that is being accessed by rows, and this is good, okay? And then we have another matrix B that is being accessed by columns, and this is bad. So you can think, let's interchange the loop. But the problem with this is that you interchange the loop, then you fix the access to B, but you spoil the access to A. Okay? So there is not an obvious solution for that. And obviously we make lots of matrix multiplication, okay, nowadays. So the idea of loop tiling is that I'm going to divide, I'm going to explain it just in plain words, okay, because it's how far I want to go with this. Instead of doing, this will be an execution of these two inner loops, okay? So the rows of one of the matrices is, yes, and the columns of the other matrices. Okay, so this is C, that is the result. This is A, this is C, the result, E, I don't know what happens with this area, and B, okay? So if we apply loop tiling, and this is the monster code that appears, instead of doing the computation as a whole, I'm going to do it by tiles or blobs, okay? And this is going to make the memory access more efficient for both matrices, not just for the one that is accessed by rows, but also for the one that is accessed by columns. Okay, so I'm not going to give you the details of how this technique works. This is a widely used technique for improving the memory performance. Most of the times when you make scientific computing, at some point you are going to want to apply blocking or tiling. If not, sometimes the compiler is going to do it for you. But what I want you to notice is the effect on the performance. So this is the original matrix multiplication. What it happens, this is the gigaflops. Do you remember this metric? Gigaflops. billions, American billions, of instructions per second. Okay? So, as you can see, in the unoptimized version, for a small matrix, the performance is very good. This is a relative performance. Okay, so it's independent of the amount of work that you have to do. Okay, so when you increase the matrix, the performance drops, and as you increase it, the performance drops even more. And the reason for this is the cache performance. When the matrix is too large, at some point, it's not going to fit in the cache, okay? And as a consequence, the processor has to wait. So this is halving the performance of the computer, okay? If we use a child version of this, what we are going to see is that the performance remains the same, okay? And the magic here is done by the tiling technique, because as it splits the computation in tiles of the appropriate size, then they are going to fit in the cache, and the cache performance is not going to be degraded. Yes? Yes. In this case, for instance, you have to multiply, I believe, this value by all these columns, okay? This is how the operation works. And you have to reuse, for instance, these values like several times, because you are going to multiply all of this by this one, this one, this one. So you want to keep, for instance, this in the cache between one multiplication and the other. If the size is too large, it's not going to fit in the cache. So it's going to be replaced from there. So when you go to access again all these values, the values of the first row, they are not going to be longer there. Okay? Because the size of the cache is not enough. Okay? Okay, so the idea of tiling is that it changes the shape of the computation in a way that is made in tiles that fit the cache. Okay? It's not, at least I want you to understand the intuition, okay? Because obviously the details takes more time to be explained. Okay, so another technique that improves a lot the performance of the cache is hardware prefetching. The idea of hardware prefetching, I heard a piece of news like, I don't know, 4 years ago or something like that, that said that Amazon prefetch orders. So he was able to predict how many, I don't know, Kindles were going to order this afternoon in Madrid, for instance. And then they create the packages for them in advance. So when the orders, the amount of orders predicted arrived, they were ready, okay? So the idea of this is the same. If I detect that in a few nanoseconds I'm going to need a piece of data, then I'm going to prefetch it, okay? So while we know that the processor and the memory can work independently and in parallel, the idea is that while the memory is idle and is not doing something relevant, it's prefetching things that it thinks that you are going to need in the near future. So when you ask for them, they are going to be loaded already in the cache. Okay, so can we do that? Yes, and actually it's done lots of the time. Imagine that I'm accessing array A sequentially, and then I start with position 0, 1, 2, 3, 4, and so on. Okay. So the processor is going to be able to detect automatically an access pattern like this, and being able to guess that in the future you are going to need A5, A6, A7, A8, A9, etc. Okay? So something that is quite impressive is that modern processors are able to analyze up to 16 prefetching patterns at the same time. Okay, so they are able to analyze the access patterns that are happening in your program and are able to manage until 16 at the same time. Okay, and this is going to imply a big performance improvement. So this is pretty old because this is a Pentium 4. This has improved a lot in the last years. And these are several algorithms or programs of the spec benchmark. Okay, so what you can see here is the improvement in times, I believe, due to the use of hardware prefetching. Okay, so this will be a 60% better, this will be a 40%, 45% better, and this is almost twice faster than the original code without prefetching. Okay, so prefetching can be done by hardware, but also the compiler or even the programmer can insert their own prefetching instructions. Okay. Okay. Now, let's talk about virtual memory. I'm going to simplify this part of the course because it's important that you understand the existence of virtual memory from the point of view of architecture, but it's not so common to think on it. Okay, I believe. Most of the time, people is not aware that virtual memory even exists, and rarely, in rare situation, is going to cause problems that can be addressed from the HPC point of view. So I'm going to explain you more or less how the mechanism works. Okay, so let's think in a computer. We are using a computer, and a program is being executed. And before we said, okay, the program can emit a load or store operation with a physical address. And as we said, a physical address is a position in the RAM memory, in the physical or the internal memory. But so when we program or encode our application, we should be aware of the current state of the physical memory. Okay, so let's start this from scratch. Okay, so this is the RAM memory. So from the beginning to the end, these are the physical addresses of the RAM memory. But we as programmers are not aware of this. And the mechanism that we have in the middle is what is called the virtual memory. Because when virtual memory didn't exist, or a single program was running in the computer at the same time, or we have several of them running at the same time, but they were aware of each other. I mean, if we have several programs, all the data and instructions of program 1 are here, all the data and instructions of program 2 are here, and all the data and instructions of program 3 are here. So each program has to be somehow aware of its location in the RAM memory. But this is not happening, okay? Probably when they send the rocket in the Apollo mission to the moon, they program it like this, okay? But when you make a program, you don't know what is going to be physically in memory, okay? And the mechanism that you have in the middle is called virtual memory. The idea of virtual memory is that each program is going to have a virtual memory space that is huge, larger than the physical memory, and that it starts at 0 and it ends at the maximum addressable memory. For instance, in 32-bit systems with 32 addresses, the maximum amount of addressable memory is 2 raised to 32 bytes. Agree with that? 2 raised to 32. If we have 32-bit addresses, then I can address up to 2 raised to 32. Anybody knows how much information is 2 raised to 32? How many? How much?
124.
Yes, but how many gigabytes of information is that? 2 raised to 30 is 1 gigabyte of memory. Yes, it's 4 gigabytes. Somebody was answering the question in the chat. It's 4 gigabytes. And that's funny because that's the reason why I believe that Windows XP, that was a 32-bit system, initially at least, could not make use of more than 4 gigabytes of RAM. And when more memory appeared for the desktop computers, what they did was to make a patch to the operating system, okay, to extend the amount of memory available beyond 4 gigabytes of RAM, okay? Now, obviously, if you have a 64-bit system, this is going to be 2 raised to 64, so we can forget about this problem for a while, okay, because this is huge, obviously. Okay, so the idea of this is that I'm going to have lots of virtual blocks in the virtual memory of a program, and some of them are going to be loaded in some locations of the physical memory, okay? Any of you study virtual memory? Anytime? Here? No? Okay. I guess that those that study computer science, at least in Spain, they study operating system, virtual memory, but this is part of the operating system, but it's kind of related to the hardware. Okay, so yes. The virtual and the physical.
Yeah, in the last.
In my figure.
Yes.
Yes, the idea is that a program is going to allocate memory in its own virtual space that starts at 0 and finishes at the end of the maximum addressable memory. For instance, in Windows XP, that was a 32-bit system, we had 32-bit addresses, so it was a maximum of 4 gigabytes. Okay? Well, so we can have here like the code of the program, we can have like arrays or data structures or whatever, but not all of them are going to be loaded at the same time in the physical memory, as we know. We just load some of them, those that fit, okay, or those that are required at a given moment, okay? So, for instance, this block can be here, okay, or this block can be in this other position. So for some of your virtual addresses, those of your program, there is a correspondence between a virtual address and a physical one. So when this correspondence exists in virtual memory, this is a hit. And when this correspondence doesn't exist, this will be a miss. And what do you have to do in that situation? You have to allocate room for the block of information and load it in there. Okay, the same that happened in the cache, but it's a slightly different mechanism. Okay, so we have like different illustrations here. Okay, so this is a single program. Sorry, I don't know what happens with this. This is the virtual address of a single program, the virtual space of a single program. These are like the different pages of that program. And then you can see that some of them are in the RAM memory, in the physical memory, but others are offloaded into the hard drive, into some positions. Okay, not all of them are in there. Actually, this is the swap space that we do have in Linux, for instance, but this is a completely different story. So the idea is that when the processor makes a load or a store operation, the address that is going to be emitted by the processor is virtual. Okay, it's a virtual address. So at that point, you don't know if the information is or not in the physical memory, in the RAM memory. So you have a translation mechanism that we are not going to explain here in detail that tries to convert this virtual address into a physical one. If the translation is possible, this is a hit. The information is in the main memory. If the translation is not possible, this is going to be a miss, and then we have to allocate a space for that information, and then to complete the translation. Okay, so this is the basic mechanism. Yes?
For example, if you have some instruction like add JS0, JS1, JS2.
Yes.
$0.
Yes, yes.
$0.
Zero, yes. Fair, está bien.
$1 and $2 is the virtual address.
No. These are registers of the processor. When you have machine code, you usually have load operations like this to bring information from memory to the registers. Then you make the operations on the registers, and at the end, if you want to upload that information back to memory, then you have a storage operation. So the address of the load and the address of the storage is the one that is virtual. But the addition itself is on registers that are just part of the processor. Okay, the registers are like an internal buffer of the processor, just to make temporary calculations. But when the processor wants to communicate with the memory, then it needs to make load or store operations. And in order to do this, it's going to emit virtual addresses. Okay? It's a bit tricky. Okay. Okay, so I'm not going to get into detail of this, okay, because as I told you, this is a quite advanced topic of computer architecture, very detailed. Okay, so something that is also relevant for the performance, and sometimes you are going to find this in performance tools is the translation look ahead buffer. So what I have just told you is that every time that you make a load or a store operation, you need to make a translation. And as you can imagine, this translation takes time. Okay, you have to pay for it because it's not, give me the translation of this virtual address. It's not instant. It requires time to make the translation itself. So in order to accelerate this process, yes. Yes.
So when virtual address have this address,
Yes.
it's a miss.
Is?
In the example,
Yes.
virtual address have a physical address. It's a hit. You say it's a hit. When you can translate virtual and physical address, you say it's a hit.
It's a hit. Yes. Yes.
But when a virtual address has these addresses, it's a miss or it's a hit?
When you can translate it,
Yes.
it's because there is a physical location corresponding to that physical address. So that's a hit. Okay?
Yes, but in the example, we also have these addresses. These addresses. The server.
I don't see it. Where is it?
These addresses, I don't know if I can. No.
It's not here.
No. Yes. No.
Here.
Yes.
These addresses. Yes. These are locations in the hard drive. But they are not like 1 and 0's locations. It's like the physical location on the hard drive. That's a different story.
So it's
It's a miss. When you find the information in the disk, it's a miss because you want it in the level where you want to take it from. That is the physical address. Okay. Okay. The physical memory. Okay. So what I was telling you before is that the last topic about the about the virtual memory that is important for you to understand is the translation process. The translation process is costly itself and takes time because I'm not going to enter into detail, but you have to consult several intermediate data structures. So in order to accelerate it, and because you have the principle of locality, you know that when you make a translation, you are going to need this translation again in the near future. Okay? Because if you need a piece of data, we said that you are going to need that piece of data anytime soon. So the same applies to the translation. If I need to translate the address of a piece of data now, it's very likely that this same translation is required in the near future. So in order to do this, we can have like a buffer or a cache, maybe this is not a good name, of translations. Okay? So the idea is that if I make the translation of virtual address 0 to physical address 5, and these are just toy numbers, okay? Then I can put this translation in a buffer, which is called translation look ahead buffer or TLB, okay? So if I need this translation in the future, I'm going to find it in the TLB, and it's going to happen faster. Okay, so this is just a buffer of the latest translation. Why this is important? Because the performance of the TLB is also a key component of the performance of the memory. Okay, because if the TLB, the translation look ahead buffer, doesn't work well, doesn't have a good hit rate, then this is going to degrade the performance of the computer. Okay? Okay, any questions? Any questions? It was a long explanation so far. Okay, so this is the end of the review of computer structures. So after the break, we are going to start with chapter 2. Okay, we are going to start with a classification of parallel architectures. We are going to classify them according to different criteria, and that's the end. That is going to be the last thing that we are going to see today. Okay, so let's get back at 6 p.m. Okay, o'clock. I'm going to give you a long break.